Again, welcome you all. Nice to see you here. Hopefully, we'll have more of people joining us soon. I'll hand over the stage to Dr. Bera to take us through Insights in Science Part 2. That is, how reliably can we compute? Thank you very much.
Thank you very much. Implied by the lecture title in a simple and direct way, these are not popular lectures, nor meant to popularize science. They are presented for the importance of the topic and directed towards those who desire to cast fundamental science into technological marvels. Throughout these lectures, you will notice that the best scientific knowledge is cast in an axiomatized form, and the precise language for expressing it is mathematics. You will rarely see complicated mathematics in the lectures, but I will try to highlight the brilliant concepts and conjectures geniuses have used to express and discover scientific knowledge. Today's lecture is devoted to understanding how one can avoid or minimize error buildup inherent in finite precision computing. So this is the lecture. Copyright information, I don't think. So it gives me immense pleasure to address this audience. In the next 90 minutes or so, I will present a glimpse of how numerical errors creep in computations because we compute with finite precision, and explain the general principles by which we might minimize them with a given precision. Before I move further, how many of you have realized that the computing that you do, the so-called real numbers that you compute, are actually real numbers that you're computing? They are not real numbers as far as the computer is concerned. The reason for that is when we talk about real numbers in mathematics, we talk about infinite precision with which we can represent a number. In a computer, we just simply do not have that luxury. Secondly, just to represent one number would require infinite resources. So for you to even move on to the next step of calculation, just adding two numbers will take an infinite amount of time. So it's not a very practical kind of a thing. It's an idealization that we make in mathematics, but it is not something that we can implement in real life. As a consequence, what actually happens in a computer is that you are simulating real numbers using integer arithmetic. But that has never been told to you, I suspect. When you did numerical analysis, I don't think your professors ever told you that you are actually doing integer calculation in a very disguised form. Okay? And therefore, you think you are doing real number calculations, but the axioms of real numbers are not actually followed when you do floating point arithmetic. Okay? So these things cause certain fundamental problems and certain very peculiar problems at times. Okay? Generally, for practical purposes, for solving many kinds of problems, you will not be aware that there is this distinction, that floating point is not real number. Okay? But there are other situations, some of which you will get to see in today's lecture, where it makes a huge difference if you cannot distinguish between the two. So the other thing that you must understand is the foundation of mathematics is logic. So if logic has a problem, then mathematics will automatically have a problem. Okay? So we begin with a paradox in logic, and it says, I begin with, is the statement I am a liar? Is the statement true or false? This is the Epimenides paradox, also known as the liar's paradox in logic. Epimenides was a Cretan who lived in 6th century BC. What happens if you write a computer program to answer the question? Okay? I think I mentioned to some of you, probably informally when we were having coffee last time, that I and the company I work for, we have just recently begun to look at the possibility of our getting seriously into some high-end artificial intelligence project. Okay, to get to the high end, there are certain things at a very foundational level in science and mathematics that we need to be very clear about. Because unless we are very clear about it, it doesn't make any sense to talk about high-end AI. Okay. So the first thing is Epimenides' paradox. Is there an AI system that any one of us knows? I do not know of anyone. To whom? To that AI program, if I say, tell me, I am a liar, is the statement true or false? I don't think there is an AI system that has been actually built keeping this paradox in mind. So eventually what will happen is you pose a statement like this to an AI system, it will continue to get into a loop and it will never be able to give you an answer. The reason for that is that if I'm a liar, now how come I'm telling a truth? And if I'm a truthful person, then how come I'm a liar? Okay, so you can see that it just gets into a loop. The equivalent of that is a loop in a program, a do loop in a program out of which you will never come out. Okay. Then, using this paradox, Gödel proved a theorem in his early 20s, I think it was at the age of 23 or so. He came out with a theorem named after him, and he said that every system of arithmetic contains arithmetical propositions, by which is meant propositions concerned solely with relations between whole numbers, which can neither be proved nor disproved within the system. In the last lecture, remember, I made one very important point. Any axiomatic system can be arithmetized. And therefore, every mathematical theorem can be related to any axiomatized system, provided you know how to map one system to the other. And therefore, it is enough for any one of us to understand an arithmetical system and see if the arithmetical system has any problems or not. If it has any problems, then we can guarantee that any other axiomatic system, unless it's an extremely trivial one, and those trivial ones don't matter because they don't, we don't get very far using those kinds of axiomatic systems. So if arithmetic has a problem, then we know, and this is what they proved, any axiomatic system will also have a problem. Okay? So any formal system that is interesting enough to formulate its own consistency can prove its own consistency if and only if it is inconsistent. Now, remember that I said it a few times in my last lecture that truth is not knowable. So you see here that if you think you have a axiomatic system interesting enough to formulate its own consistency, can prove its own consistency if and only if it is inconsistent. So you see the Epimenides paradox is rewritten in a different setting. Okay, you have a paradox here that if I claim that my system is consistent, then I can prove it only if my system is inconsistent. Okay? So truth is not knowable, but why have results like this have not led us to abundant science or even abundant logic or even abundant mathematics? The reason for that is rather interesting, that in the circumstances where we apply them, with a little bit of our instincts and common sense and so on, we somehow are able to find out when some things tell us that we are obviously wrong. Okay? And therefore we just tend to stay away from it. It's a psychological thing that we build up. It doesn't work there. We have tried to understand why it does not work there. We have not been able to figure out. We give up after some time. Okay, it works in these many, many areas, which has given us the civilization. It has given us the air conditioning. It has given us all this. It works. So, I'm quite comfortable with the fact that it works and it makes my life better. So many of us sort of have adopted that very practical attitude. It is only when you are a researcher in the class of Gödel that you ask these questions and then you point out that there are problems ahead. Now, soon after Gödel, Alan Turing, who is supposed to be the father of computer science, he showed that there is no general method by which one can decide in advance if a computer program will eventually halt. As a corollary, he then concluded that there can be no way of knowing it in advance by reasoning either. So he is reiterating that Gödel was right. Logic is the foundation of mathematics, and Gödel said that there are things that you cannot do. And that is what he's saying. There are computer programs about which you cannot say something very precise. So as a corollary, he then concluded that there can be no way of knowing it in advance by reasoning either. That is, I give you a computer program and you cannot give me a formal mathematical proof that this particular program is going to stop or not stop. This is known as Turing's halting theorem. So that is, there is no formal axiomatic system which will enable one to deduce in advance whether a program will halt or not. The real problem lies in those programs that will not halt, and that is the dilemma of not knowing when to give up. So you keep running the program and then it doesn't halt. You're left in a dilemma. Should you wait until you drop dead or should you give up? It's a hopeless case. The dilemma is that you don't know if you had continued just one step more, then you would have got the solution. Okay, so you are perpetually in that state of a dilemma. So note that while Gödel had looked at one particular axiomatic system, that is arithmetic, and that it is incomplete, Turing said something more. He said no formal axiomatic system can solve the halting problem. So essentially what we are saying is we build our knowledge on the basis of an axiomatic system we begin to trust. We can never ever prove that that axiomatic system will not create paradoxes. What Gödel says is there will be paradoxes. If you have not hit upon one, you're lucky. But if you hit upon one, we hope that it doesn't destroy your world. Then there is this fundamental theorem in arithmetic, which is one of the most amazing theorems that I have come across. It says every whole number greater than 1 can be written as a product of prime numbers. And actually, it is this fact that Gödel used when he proved his theorem. He used this very theorem. It's at the foundation. It's called the fundamental theorem of arithmetic. That every whole number greater than 1 can be written as a product of prime numbers. Computation means going from one integer to another, and in one of the slides in my last lecture, I said, what does a computer do? And I said that it does only one thing. It goes from one integer to the other integer, and the integer contains all the information that the computer needs to go to the next number. Any axiomatic system can be arithmetized and hence can be implemented in software. All program and data, when placed in a digital computer's memory and registers, is represented in principle as a single binary string. At any given instant, this string essentially represents an integer. After each machine cycle, this integer changes to another integer. Digital computation is all about going from one integer to another according to a set of rules embedded in the integer itself. But these rules that are embedded in the integer itself is interpreted by the hardware. Okay? So it is like saying that God has created this universe. You know, you can think of the universe as a computer, but the hardware is actually encoded in some other way, which are the laws of nature. So the laws of nature knows exactly, whatever information the universe at any given time has, embedded in that information is where the universe should be at the next instant. So in the world of finite computers, real numbers can be represented only approximately. The approximated real numbers are called floating point numbers. And a set of floating point numbers F is characterized by 4 parameters, just 4 parameters. That is the number base, beta. It can be a binary system, it can be a decimal system, hex, whatever base you might decide to choose. And the precision T, that is the number of digits, significant digits that you're going to carry, and the exponent range, that is the smallest number and the largest number. And each floating point number x in F then has the value represented as, you would have seen, we represent floating point numbers typically as decimal something, 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 and then the exponent to the power something. Okay, that is the standard format in which we put. So this is decimal something, something, something multiplied by, in Fortran we used to say e to the power of something, and in other languages also I think we typically say that. Where the integers d1, d2, etc., they satisfy. What essentially it means is that a whole range of floating point numbers are grouped together and represented by one floating point number from among them. So it's like rounding off things, we go and do our shopping, and it comes to, your bill comes to, say, 5.32 rupees, and then you sort of round off. You can either do it 5.3 or you can say just 5, whatever. So all of those, anything following the decimal sort of gets clubbed together into a single number. So every floating point number on a computer actually represents a group of numbers. If you want to be very, very precise about it, it actually represents an infinite set of numbers. Because each number, one of the things about real numbers is that if I give you a real number, you cannot tell me what is the next real number. Because whatever number you give me, I can give you one that lies between my number and your number. Therefore, mathematicians call these numbers as uncountable numbers. That is, you cannot, given a real number, you cannot actually tell me what the next number is. That is not true of integers. If I tell you 2, then you can tell me that 3 is the next number. Okay? And 4 is the number after 3. But in real numbers, any number I give you, you cannot tell me the next number, because I can always give you another number in between. And you can keep on doing it forever. So that is why real numbers are not countable. Whereas integers are countable, because I can go from 1, 2, 3, 4, 5, 6, 7, 8, etc., etc. Okay? So in that form where a floating point number is represented, remember that in a binary system, this will be 1 bit, the next bit, the next bit, and next bit, and so on. It will be either 0 or 1. Okay? So in that form, if for every non-zero x in F with the d1 not equal to 0, that's a condition to normalize the number, and so that everybody comes out with the same format and same understanding of the number. So d1 not equal to 0, then the floating point number system f is said to be normalized. The integer e is called the exponent, and the number this is called the fraction. So this is a mere definition, and none of you should have any difficulty in understanding this. But if you have any difficulty, I can tell you one thing absolutely straight away. Your teachers have done a bad job of teaching you. It's not necessarily your fault. Your teachers have done an extremely bad job if you have not understood up to this point. Okay? But fortunately, the rest of the slides can ignore the fact that you may or may not know this. Okay? While the real number system is not countable, the set F is finite and countable. And because it is countable in mathematics, you can show that you can create a one-to-one correspondence between this floating point numbers and the number of integers. Okay, it's like giving a serial number or whatever it is. It has exactly these many numbers in it. That is a given computer. These are equally spaced throughout their range, but only between successive powers of beta. Moreover, each number in F has to represent a whole range of real numbers. Clearly, if F is a finite set, there is no possibility of representing the continuum of real numbers in any detail. Indeed, real numbers whose absolute value is larger than the maximum number of F cannot be said to be represented. For example, you really cannot represent infinity. And for many purposes, the same is true of non-zero real numbers smaller in magnitude than the smallest positive number of F, which also means that you cannot represent minus infinity. So in modern digital computers, the conversion of decimal numerals to binary is not always exact. By increasing the precision with which arithmetic operations are done via binary mappings on decimal numerals, such a loss of exactness can be reduced, but it can never be eliminated. This creates problems when two decimal numerals are compared and an exact comparison is desired. During computations, correct results from such comparisons cannot be guaranteed if the compared numerals are very close to each other. Okay? So if two numbers that you have in mind, they differ very slightly, but they're categorized by the floating point system to be the same number, then obviously, you will not know that there was a difference. This is not a problem with integers. With integers, two integers are given, you will always be able to say which one is, if they are equal or not. Okay. Now, in certain areas, certain kinds of problems where I require this high level of precision, where I really want to be pretty sure that this is equal or not equal, I sort of try to recast the entire formulation in terms of integer arithmetic. Because in integer arithmetic, then I will not be facing that problem. But if I'm doing it in floating point calculations, then I can get into a kind of problem. Because if same numbers belonging to the same designated floating point number, if I try to compute them and your result is sensitive, it can happen in a very unstable situation where you have to be very, very aware of minute disturbances. Then a floating point comparison is dicey. Because you might run the program with a certain precision, and when this comparison is made, one program may say go there, and the other program, because of a different precision, says you go there. Then you're branching off. And therefore, what you calculate and what somebody else calculates, they may be entirely different. So unless we are aware of these things in certain systems which are very critical to these kinds of comparisons, then there could be very serious problems. So Lest we forget, the badly named real number system underlies the calculus and higher analysis to such an extent that we may forget how impossible it is to represent all real numbers in the real world of finite computers. So you can see that calculus depends on something, some entity that we call as infinitesimal. The infinitesimal is a very interesting kind of a creature. When you were taught mathematics, at least when I was taught mathematics, and one of the grudges I have against my former teachers is that I think they taught me all kinds of things which I did not need to be taught, and they forgot to teach me certain kinds of things which would have been invaluable to me later in my life. Did they ever tell you what follows after zero? They never told you that, right? Newton figured out what it was, but then I don't think he ever sort of emphasized that point. He left it to other mathematicians to sort of intuitively understand this fact. What follows the zero is the infinitesimal. And by definition, the infinitesimal it is as small as you can imagine. Okay? So, in real numbers, you have been told what zero is. You have told a lot of other things. You have been told about rational numbers and irrational numbers, but somewhere along the line, I don't think, at least none of my teachers ever mentioned it, that there is something called the infinitesimal. Yeah. Yeah, zero has been discovered. Zero was discovered in India. The reason I probably will not talk about zero and or infinity today, because they are governed by different sets of axioms. They are not governed by the same axioms that non-zero and non-infinities have. So every time I did mention this fact in the last lecture, that when you're dealing in arithmetic and you have to deal with zero, I'm not talking about 1.002, I'm not talking about those zeros. I'm talking about zero by itself as the number, and infinity by itself as the number. These numbers are governed by different axioms. So if they appear in any kind of a calculation, you should immediately stop everything and I say, I have to think in terms of a different set of axioms related to this. Okay. For example, 0 into 2 is 0, 0 into 3 is 0, but 2 is not equal to 3. Right? So these are obvious examples, but there are other examples where you can sort of, if you're unaware of the fact that these are governed by different axioms, you can get into serious trouble. So the named real number system underlies the calculus and higher analysis to such an extent that we may forget how impossible it is to represent all real numbers in the real world of finite computers. However, as much as the real number system simplifies analysis, practical computing must do without it. So, for example, the floating point number 0.1 summed 10 times does not result in 1 in a floating point number system for which the number base is a power of 2, that is a binary system, because 1 by 2 does not have a terminating expansion in powers of 1 by 2. It's an infinitely long binary string. Okay, it's like 1 by 3 in decimal system is 0.3333 forever. But at least you know it is forever. But if you talk about pi, then you actually don't even know what the next digit is. You have precision up to n, but you cannot tell me what n plus 1 is unless you compute it. Now, the floating point, the operations of floating point addition and multiplications are commutative but not associative. But for real numbers, they are associative. And the distributive law also fails for them, since these algebraic laws are fundamental to mathematical analysis. Analysis of floating point computations are very difficult. And remind you, the laws in question are the commutative means x into y is equal to y into x, or if star is any operator, that relationship holds. The associative thing is that that relationship holds, and distributive is that that relationship holds. Now, even when we do floating point calculations, we somehow assume that these laws also hold. At least we don't consciously remember that these laws probably do not hold. They seem to hold. It doesn't generally make much of a difference, but there are situations where it makes a difference. And the consequence of that is that you may write a computer program. I will say there's nothing wrong in the computer program, but if I switch the operations, like if my computer program has this, I get one result, and if the same statement x into y is written as y into x, then I get a different result. You can look at the program day in and day out and ask millions of your friends to look at it, and nobody will ever spot that there is a problem there. Because what does not strike them is that the commutative operation does not work in floating point numbers. Okay, now here is a dramatic example of this. We know, and I'm sure that you may not remember the exact formula, but you know that e to the power of x has a infinite series expansion, and that is that. Now consider a floating point system characterized by beta is equal to 10. That is, we are using the decimal system, and we are doing arithmetic using 5 significant digit calculation. For x is equal to minus 5.5, the following successive terms are produced. And I'm sure when you were learning computer programming, calculating a series would probably have been one of the earliest programs you wrote ever. To tell you how to do a do loop, you would say, sum is equal to sum plus term, term is this, and so on. So if you wrote a program like that, and I gave you an input, minus x is equal to minus 5.5, and I say, okay, what does your computer program say? Now, this computer program would give successively these numbers, term by term. Okay? Now, calculated up to 25 terms, since subsequent terms no longer change it. So after this, even if you calculate with 5 significant digit computation, nothing is going to change. Okay? So you sum it up, and e to the power of x for this particular value of x turns out to be that number. Now, it just so happens that the correct answer is something completely different. Okay. So, this problem will arise if you use, say, single precision in your computer. This problem will begin to arise at x is equal to, say, maybe 20, minus 20, or 15. Or if you use double precision, it may appear at a slightly later stage. But the problem is that you will literally have to go to very high precision, for which computers do not exist yet. And if you wrote the program just in that simple-minded manner, then you are guaranteed to get wrong results sooner or later. Okay? And you will not be aware of it. Of course, after attending this lecture, you will become aware of it. But so, this is what you calculated, and this is what the blue one is the actual result. So the computer result actually has no significant digits. You cannot trust even the first significant digit in the result. Now, what are the sources of error here? several terms and consequently intermediate terms are several orders of magnitude larger than the final result. In fact, terms like 38.129 that you saw in the previous slide already have round of error which is nearly as large as the final error. This is the primary source of error. Remember that conversion from real number to floating point numbers, there are going to be errors. The above errors are magnified by the loss of significant digits when differences are taken of numbers which are similar in magnitude. Like what would be the difference if the two floating point numbers are designated by the same number with your precision? Then the difference will always be zero, but it is not really zero. And those differences will eventually, in a set of computations, can build up very rapidly under certain circumstances. In this case, the error has actually built up extremely rapidly because even for x is equal to minus 5.5, within 10 or 15 terms, you have seen that you simply cannot trust the result. So an obvious remedy is calculated with much higher precision. However, it is a luxury that we do not always have. I mean, I cannot compute carrying 1,000 digits in my computer. Even a government will not be able to afford buying that computer. It is not that we cannot do. One of the programs that I have, and I also have a patent on that set of arithmetical calculations, where I can set the precision for my calculation to whatever level I want. So if I want to carry 10,000 digits, significant digits, there is nothing to stop me from doing that. My program will do it. Okay, it'll take its own time doing it. That's a different matter. For this kind of a 1,000-digit precision, with the kind of computers that we have, the fastest of them, it is calculable if the calculations really depend on that kind of accuracy. It is calculable. Okay, but you need a very specialized kind of software to be able to do that kind of a thing. Yeah.
What we used to do is we were using strings to, compute large multiplications. So we were back in class 10th. We were using strings to actually compute large multiplications or divisions. Of course, we never ventured into floating point. So, I mean, the program that you are talking about, is it something similar? So,
Okay. It is completely string manipulation.
Got
It's
it.
completely string manipulation. And in fact, you were not here in the last lecture.
No, sir.
Oh, okay. I had talked about strings.
I see.
I talked about strings in the sense that all axiomatic systems, essentially what I was telling them is, essentially it is a string that you're dealing with, a string of symbols, and then the axiomatic system tells you what kind of rules are to be used for manipulating those symbols. So the core of axiomatic system is a set of symbols, a set of rules, and string manipulation.
Got it.
Your point is very well taken.
Thank you.
So smart remedy is, surprisingly, if you're alert to situations like this actually can be calculated to much greater accuracy by just writing this as over e to the power of 5.5. So here you're calculating e to the power of not minus 5.5, but e to the power of 5.5, and then you're taking 1 over that number. Okay. Now, if it is a positive integer, presently, these errors don't happen that rapidly. They don't grow that rapidly. They still grow, but they grow at a much, much slower rate. And therefore, if you do this calculation, you get that result. Okay? So the simple trick here is, if you are writing an exponential program, you say, if the exponent is negative, then calculate it this way. If it is positive, calculate it in the normal way. Okay? In this particular case, the remedy happens to be extremely simple. If you know it and you are aware of it, then, anyway, most of you would not have been aware of this problem for the simple reason that the exponential function is a library function. And people who created these libraries, they have been aware of these problems. And therefore, your library takes care of it, so that is the reason you never face that problem. But if you wrote your own exponential function routine and did it in a simple-minded way, you would be having all kinds of problems. Okay, yeah.
Sorry, one more question. So, can we actually analytically prove that if we computed E minus 5.5 versus 1 by E 5.5, then there's going to be a difference in the error? Analytically, we can actually...
Yeah, we can do that. In fact, I will come to the name of the person who actually started all this business. And then for doing this kind of a thing, he got the Turing Award. And I think he also became a fellow of the Royal Society.
I see. And so just one more question. So we have all this modeling or all these simulations that different R&D organizations across the world, the government included, are doing. So I mean, most of the times they are working with large number sets.
Yeah.
And of course, there are floating point digits there. So I mean, are we saying that most of them are actually using string manipulation, or a large number of them might actually be using, standard libraries within C++ or other languages to compute, so where an error can essentially creep in? So any
comments related to that?
Yes.
Yeah. My comment is that if you're using a library, then try to buy the best possible library that's available in the market, and their most recent version, because they're continuously trying to refine and take care of these problems which a normal programmer or a normal numerical analyst will not try to take care of. So they build their libraries with a great deal of caution. If you don't spend that kind of money, then, and I'm aware of it, and you give me computer results and you tell me this was a program, and I spot there are places where you've done kinds of computations where I am a little skeptical, I would not trust your computer results. As simple as that. Prima facie, I will not trust your results because I know your results can be absolutely wrong. Okay? So, in situations like I said, because these are there was a time in my career when I became quite concerned about these problems because of the nature of the problems that I wanted to tackle. And I wanted to be quite sure that, so that is when I began to start programming using string manipulations. Okay? And using string manipulations, obviously, I was not dealing with numbers per se. It can always be done with the numbers, but it was essentially a symbolic system, not even algebra. It was purely a symbolic system. So when I have to tread very cautiously, then I fall back on the things that I trust and where I can control the errors. So one can show, now here is another example, which one does not normally suspect that my computer program would give an incorrect result, where I have relied on my power of programming things. One can show by integration by parts that this particular thing, E1 is equal to 1 by E, En is equal to, etc. There's a recurrence relationship. Use the recursion relation with numbers base beta is equal to 10, that is the decimal system, with the precision t is equal to 6 to compute the following. And these are the results that you will get. Now, you look at the results and something very surprising happens. And that is E sub 9 is negative. You suddenly the integrand is positive everywhere. So how does the integral come out to be negative? See, look at that integrand. X to the power n, x is positive everywhere. X minus 1, e to the power of x minus 1, that is positive everywhere. So when does the integrand over that interval start becoming negative? So, not that the recursion formula is exact, the only source of round of error to begin with was in calculating E1, where 1 by E was rounded to 6 significant digits, and this error is about delta less than a million, 1 in a million. How did this small error get magnified? You would have thought that, well, I can live with the error of this small size. And notice that in the recursion formula, this is multiplied by n. So your error is being multiplied by n. And at every step, it is being multiplied by n or n minus 1 or n minus 2 or n plus 1 and n plus 2 or whatever it is. That is a factorial function. At each step, the buildup of the error is following a factorial function. You take factorial 2, it is 2. Factorial 3 is 6. Factorial 4 is bigger, and pretty soon, it gets out of your computing range. You cannot calculate, if I'm not mistaken, you cannot calculate factorial 100 on your computer. So that is the source of the problem. The successive numbers are being multiplied by a factor, and that factor is actually increasing in a factorial form. And therefore, every bit of error is getting magnified by an increasingly larger and larger number. And because of that, you saw that very funny result that at least the program should be decent enough not to give you negative results, but it even gives you negative results. So a smart remedy, rewrite the recurrency relation as go backwards. Don't go starting from E1, E2, E3. I'll start from some distant E, say E40 or something, and then I'll start going backwards. Now you realize what's going to happen. Say something was being multiplied by 40 factorial, then the one previous to that would be factorial 39, then it will be factorial 38, then it will be factorial 37. So your error is actually decreasing along the way. Okay? So instead of the errors going upward, the error starts going downwards, and then I've told you the solution, but I was supposed to have asked you to think about it. Okay? So that is what is happening. It is being divided by this number, which is... Then you might say that, look, in this particular case, I don't know what is a large enough n. Okay, so choose whatever you want as a decent n. Okay, and so in this particular case, I think what was done is choose, in this particular case, we arbitrarily said n is equal to 20, and E20 is practically set it to 0 because it's a small enough number. So you set it to 0, and then use with that approximation, you can choose n and set that E sub n to 0 with as little error as you want, and then start going backwards from there. You have a rough estimate of making that, because at a large enough n, that would be the result. So when you do that, you see that indeed by E15, the initial error has been completely damped out. We have a stable algorithm. So in the earlier cases, we had, because the error was building up in a factorial manner, So, by definition, that kind of a behavior in any system where a slight disturbance increases very rapidly is an unstable system. That is, it makes no attempt to get back to the right track. Okay? Whereas here, you see that it is trying to get back to the right track. Okay? Now, one of the things as a researcher, it took me years of sort of learning, but if one talks about an unstable algorithm in mathematics, it is no different from talking about an unstable physical system in real life. If your machine becomes unstable, then your mathematical model will also show some kind of instability. Okay? That is how, in high precision computing, when we are dealing with complex systems where we need to know whether the system is going to be unstable or not, in our mathematical modeling, we have to be very careful about how we go about computing it. Because we may, by being a little uncareful about the way we are coding and choosing our algorithms, we may have inadvertently introduced instability that actually does not belong to the physical system itself. Okay. So notice that if in the equation this, the right-hand side was slightly altered to x minus 2, the whole square is equal to 10 power minus 6, and this small change will produce a change of 10 power of minus 3 in the roots of x plus or minus 10 power minus 3, and the problem becomes worse for polynomials of higher degree. Okay. Now, the roots of this particular, you can always create a polynomial of your own, whose roots you already know. Okay? You cannot think of more simple terms than having a polynomial where the roots are 1, 2, 3, 4, 5. Yeah.
One more quick question. So we were talking about string manipulation and using the regular standard floating point functions.
Yeah.
Right. So all these results that you are showing are for string manipulated, or it's the standard function. I understand these are all standard functions.
These are using arithmetic. This is using
Standard arithmetic functions.
Yeah.
Okay. And just trying to understand. So we actually design computers for customers to model or to run different type of simulations. So I mean, if you're running the same exact algorithm or piece of code on one machine, let's say it's still 64-bit. Purchased in 2019 versus another maybe i3, i5, i7 or a Xeon CPU, are you observing different results for the same, exact same piece of code?
No, I think I understand the problem that you're referring to, although I have not worked in those areas. But if I understood the problem correctly, and if I suspected something, the results I'm telling you are the results that I already know because I've studied them and other people have studied them well and they know the remedies. Mm-hmm. So if these are the problems, then I probably will look at the remedies available, and if it is acceptable, I will use it because this would be a faster way of computing. On the other hand, there are other situations where I may not know and I have a doubt. I will automatically fall back to string manipulation automatically.
I see, makes sense.
And then there I have certain ways of going about it. Okay, I may want to approximate a function with another function whose behavior I know very well analytically. Okay, and I know that the errors involved between the two is something that is acceptable and probably even to a certain extent correctable in the sense that I can reduce the error. I may not eliminate it, but I can still reduce it further.
I see.
Okay.
And just one last question. So when it comes to computation time, so versus string manipulation versus regular arithmetical functions, so I mean, Of course, it will depend on the problem, but if the problem is essentially the same, so are we talking about like one takes 6 hours, the other string is taking 2 days, or I mean, any
No,
rough-
that would actually depend on the problem that one does. And now that we talk about AI and things like that, I would, as I'm developing any particular code of this kind, I would be quite alert to the fact that I'm doing it this way. And I will try it on a small prototype first to make sure that it works. And then I will try it on a larger scale and then try to get a feel as to how the time sort of increases. If it tends to show exponential type of a behavior, then I would have to sit back and then I'll have to ask myself, how do you tackle this?
paper or any research paper or publication on this specific?
Okay, by me, no. But for the string manipulation thing, I have a patent on that. It is owned by IBM. I used to work for IBM at that time. It's owned by IBM, but I think the patent either has expired recently or is about to expire. So if you look up the patent application, you're free to use it now without
Correct.
licensing it. But there is, but I showed in principle these things can be done if you have enough computing power. So today, if I revisit that thing, I would now see if I can optimize the string manipulations themselves, and is there some way by which I can, for example, be smart enough and say that at various points I can tabulate the expression, so whatever it is that I'm getting, and then I know how to interpolate between these tabulated entries. I might be smart enough to figure out a algorithm that does that. That would enormously speed up the thing. Okay, so something that might not be doable with available computing power, it might suddenly become doable. So I would be looking at things which, within available resources, whether I can do it or not.
I see. Thank you.
So these are the rules. I can tell you one thing straight away. If you try to get the roots of this polynomial, whose roots you know, you won't succeed. And that I can straight away tell you. You'll get all kinds of funny results out of it. And I will show you the kind of funny results that you get. Here, you're doing a binary calculation and with a precision of 30 significant digits. So how do you expect errors to propagate when a change in the 30th significant base 2-digit is made in only one of the 20 coefficients? Only one of the 20 coefficients. Okay? And assume the coefficient of x to the power 19, which is minus 210, is changed to by that minuscule amount. And see what are the results that you get. 1, 2, 3, 5, 6 is okay. 7 is okay, acceptable. 8 is also acceptable. 9 is you're beginning to become a little uneasy. 10 has become a complex number. Holy smoke, what am I doing? Where am I going? And after that, a sequence of complex roots. And notice that the imaginary part is not small. Okay? So now what do you do? So the only time, first of all, I would typically not venture to find the roots of a polynomial of 28 degree, normally. Unless I am sort of pretty sure as to where the roots might be. Okay? In which case I might use special strategies to zero in onto that particular root. But there are other situations where even that may not necessarily work. We learned a few decades ago that this problem can arise to as simple a polynomial as a cubic. that if you want to find the 3 roots of a cubic equation, calculating it numerically can, under certain circumstances, be very dicey. Very dicey in the sense that you have a statement in your computer program that says that if the error between the 2 iterations is less than this, then, stop your computation there. And you might discover that there are times when it just keeps on oscillating. It just continues to keep on oscillating. It doesn't. You don't expect that from a cubic equation. Because for a cubic, you can actually get analytical results. So if I have to deal with a cubic, I would never use a general purpose root finder. I will always use the formulas that give me the actual roots. Okay? It just so unfortunately happens that up to a polynomial of degree 4, there are analytical solutions for the roots which you can use. Beyond that, there are no analytical solutions, and therefore you necessarily have to fall back on numerical techniques. And therefore, if you're using anything at any time, numerical techniques to get the roots of polynomials, then I think, unknown to yourself, you may be courting danger. Now, what is the source of the problems? And the problem here are not due to round-off, not due to the algorithms used to compute the roots, but due to the sensitivity of the problem itself to very small changes in input data. We now understand this phenomenon much better because we understand what we call as chaos theory. And one example of chaos that I gave in my first lecture was that I showed you the behavior of the logistic map. I also showed you the behavior of what is known as the Mandelbrot set. Okay? At the boundaries or at the bifurcation points of the logistic map, you have all kinds of problems. And those are the problems that sort of show up in a situation like that. That is, the slightest error that you make, that error can lead you to all kinds of places where you never expected to be. Okay. So this is the way the error is building up. And you can say that at each root I is equal to 1 to 20, these numbers provide a direct measure of the sensitivity of each root at alpha. So you take the derivative of that and you calculate the derivative, and you say that first, second, third root, you can begin to see that the error has begun to build up from here and see where it is going. Million, trillion, whatever you want. Okay. So calculating roots of a polynomial is not one of the simplest things to do. And if you're doing it, and depending on a library function to do it for you, I still would not trust the library function unless I know more details about the code that it embeds. Yeah.
Yeah, just one quick question. So we've been using MathWorks, MATLAB, and some of the libraries there, and we've been using things like CATIA or SolidWorks, right, for thermal stress, for very, very advanced engineering, right? So I'm just trying to understand that we are not working in, tens or 50-digit decimal, but certainly in 5 to 8-digit decimals. So, I mean, again, we are trusting those numbers, those simulations, those calculations, and designing the equipment. I mean, maybe for modulating electron beams or things like those. So I'm just trying to understand that how do we figure out that whether there is an error that might be creeping in?
Okay, that's a good question. There is no standard method by which, at least known to me, by which it can be done. But one thing as an engineer that I would know, and also as a researcher in science, if the results generally turned out to be dependable for your design purposes, then probably those errors at that level are not happening. Okay. Otherwise, you probably would have ended up getting results which are going haywire. You cannot trust. If you are able to trust your results against, say, experimental data or something like that, and they look, acceptable, then probably the errors are not building up, or errors are canceling out, or inadvertently, the process itself stabilizes.
But these are very, very complex differential equations or polynomials, right? And I mean, it's not so straightforward,
No, they're actually typically the kind of algorithms and the equations that you're using and the approximations that you are making. Typically, one simple precaution is taken. We generally stay within an envelope where we know the behavior of the system. We don't expect to be unstable. We don't compute in unstable areas. So we generally know the envelope within which we need to stay within ourselves. And then somebody, some researcher, maybe in the past few decades or maybe a century earlier, has said that if you do these approximations, then I can give you reasonable assurances that the system is going to remain stable to computational errors.
So that's probably the reason why we compute only till fifth order or...
Yes. See, people do these analysis before, they commercialize a code and give it to you. In aerospace, if you're dealing with an aircraft, you cannot afford some of the luxuries of safety factors to be embedded on the aircraft. Correct. The aircraft wouldn't fly because it would be so heavy after taking care of all the safety factors.
Correct.
Okay. So we are usually assured, because other researchers have shown that these equations, even under these complex situations, say you're using a finite element method or finite difference method, they have shown that usually the analysis is linear, and therefore you're usually required also to stay within the linear range of whatever thing you're using, or at least piecewise linear.
I see.
So in the 1970s, it was discovered that numerical determination of the roots of even a cubic has problems. Now the person who actually made us aware of this thing this is what George Forsyth, one very famous mathematician and numerical analyst, said. In my opinion, Wilkinson is single-handedly responsible for the creation of almost all of the current body of scientific knowledge about the computer solution of the problems of linear algebra. So, because we are pretty confident about linear mathematics, and most of the time your algorithms would use linear mathematics or approximate it reasonably well with linearization. So this is where Wilkinson's work has become very important, because it allows you to make those approximations with a considerable degree of safety. So during this period, Wilkinson was Alan Turing's assistant at the National Physical Laboratory, London. He was a fellow of the Royal Society, so my memory was not bad, in 1969, and received the Turing Award in 1970. Okay. The NAG began work in 1970, and much of the linear algebra routines were due to Wilkinson. So, when I was at a much younger age, the NAG library was considered to be one of the best libraries for computing. Now, let me take you on a tour of how mathematicians go about their way outside of these techniques. And these are some of the techniques that I have found very valuable. They're not easy to, but if you know about them, then you sort of go looking for examples like this, then over a period of time, you also will begin to develop an intuition about how to do these things. And that intuition is extremely important if you can develop it. So find a natural number, non-negative integer, that is not the sum of three squares, natural numbers, and we now try each natural number in turn, starting with 0 to see if it is the sum of three squares. Obviously, we need only consider squares that are no larger than the number itself. Thus, for each natural number, there are only finitely many square numbers to try. We begin with 0, 1, 2, 3, etc., and quickly see that the number 7 is not of three square natural numbers. Okay, so this is good. This is what we typically do. Unsolved problem, we try a few things. If you're very lucky, we get the answer. It works or it will not work. Okay, so consider yourself very lucky in that kind of a. But if you have been so lucky, then so will probably most other people also will be similarly lucky. So there's nothing particularly, you cannot be classified as a genius according to that. Find a natural number that is not the sum of four square numbers. For in example 1, we try one number after another like this, and it turns out that the computations will never stop, for there is no such number which is not the sum of square numbers. Okay, but you have to know that. If you were not told that there is a proof to this effect, you would spend, just the way people are trying to find out about prime numbers. They're still trying to find out certain properties about prime numbers by just brute force calculation. Okay, it turns out that the computations will never stop, for there is no such number which is not the sum of squares. This was shown in a famous theorem first proved by Lagrange in 1770, and the proof is not at all easy. Okay, at least the known proofs are not at all easy, and therefore if you come out with a proof for a problem like this, you do become famous. Now find an odd number that is of two even numbers. I say, what rubbish is this here? What number with the sum of two even numbers? You don't even have to think, because it's so ridiculous. Find an even number greater than 2 that is not the sum of two prime numbers. In this case, it is likely that the computations do not terminate, but nobody knows for sure. It depends upon the famous Goldbach conjecture put forward by Goldbach in a letter to Euler in 1742, in which he wrote, at least it seems that every number that is greater than 2 is the sum of three prime numbers. Now, nobody has yet falsified this particular conjecture. And this result has been rather important to mathematicians, and therefore there are certain proofs in mathematics which just say, if Goldbach's conjecture is true, then my theorem is true. Okay? And typically so far, nobody has found a fault with those theorems because of his assuming this to be so. The conjecture remains proved to this day. Nevertheless, many results have been proved, assuming that the Goldbach conjecture has been proved, or treated as an axiom. Now, remember that in my first lecture, I talked about axiomatic systems, and I said that an axiomatic system begins with a set of beliefs. So what mathematicians essentially have done is, okay, there are all these axioms about numbers, integer numbers. I will add, which is not a part of the standard integer theory, number theory, I will add Goldbach's conjecture also as an axiom, and then proceed. Okay? But the problem is that at the back of your mind, you have this feeling that it has to come out from the original axioms. This is not a genuine axiom that we can assume. Find a natural number. So what did we learn from this example? Find a natural number, etc., etc. We learned that computations, for example, 1 will end rather quickly. For example, 2, we have a proof that it will not end. For example, 3, it will end was rather obvious. Example 4, we still have no idea if it will end at all. And this was one style of proving, that is by actual computation. Let us now look at another style. So find the of successive hexagonal numbers starting from 1 that is not a cube, and a hexagonal number is given by formula 3n into n minus 1 plus 1. And it has the interesting property that given n sub n points, one can arrange them in a hexagonal pattern with n spheres to a side as shown in the figure. Okay? So, the way to draw this is actually to use this formula and you'll be able to draw it. That's no big problem. Okay, each hexagonal number can be obtained from the one before it by adding a hexagonal ring around it. That's all you have to do. So what can we say about computations concerning example 5? Will it or will it not end? We will show by rather unusual means that it will not end. This will also mean that n sub j summed from j is equal to 1 to j is equal to 10 and will always be n cube. So if you can prove that it will always be n cube, then obviously you know that brute force method will never end. If you're in doubt, it will never end. But if you can visualize that the hexagon, the number of balls there also represent n cube, then there's no problem. You're not providing an algebraic proof or anything like that, you're just doing it visually. The figure shows a cubic array of spheres. If you look at it, can you see the hexagon? You can see the cube, depending upon your state of mind or your preconditioning, you can see both the hexagon and the cube. You jolly well know that the cube has all those things on the three surfaces. Okay, so just by looking at it, if you could make that connection, that hexagon and the cube are related in this way, then you solve the problem. Now, how do we know that? Because from a given cube at each iteration, leave the three faces as shown, leave this, and you pull out this one. And this, and this there will, if you take a projection, it will look like that. You started off with this, and you took out the shell that comprises three sides, and you keep on doing it, and each shell is a hexagon. So now you know that the hexagon and the cube are related in a very, very definite way. You have not done any algebra, you have not done anything, you have just, this is the kind of thing which I sometimes say that even a smart housewife will probably figure this out. But, typically we don't figure it out because we are so, we develop tunnel vision, and therefore we don't try to look outside of the tunnel. But if you learn from these examples that you can bring in your intuition and image processing ability of the eye and the brain, the retina is also a part of the brain, you can actually do a lot of very interesting stuff there, and probably do it much more convincingly and much more easily. If desired, one can provide a more formal proof, and an essential part of which might be the principle of mathematical induction. You see that every time you're taking out a shell, the shell is the same shape, except that it's a different scale. Mathematical induction is a procedure for ascertaining the truth of statements that apply to all natural numbers on the basis of a single computation. In essence, it enables us to deduce that a proposition P of n that depends on a particular natural number n, such as the sum of the first hexagonal numbers in n cube, holds for every n, provided that we can show first that it holds for some real value of n, and second, that the truth of n implies the truth of the next. Okay? So I will not provide an induction proof for example 5. Induction is mentioned here to bring to your notice that surprisingly, mathematical induction is not always sufficient to establish the non-stopping nature of computations. This fact is related to Gödel's theorem and to whether it is possible to say that a Turing machine will halt when carrying out certain computations. If a Turing machine cannot solve this problem, then, of course, this problem is unsolvable. Now comes algebraic invariance, and if you're going to attend my next lecture, which is on symmetry, then pay some attention to this slide, because invariances and symmetries are very, very closely connected. We have a transformation x is equal to x prime cos theta minus etc. and y is equal to that, and L which is equal to, which represents ax plus by plus c. On substituting for x and y using TL, we get this where a is equal to this and a prime and b prime is equal to this, and therefore it follows that a prime square plus b prime square is equal to a square plus b square. Now what you notice here is that the structure of the formula is the same. All you have done is, in algebra you can replace any variable with any other symbol. As long as you consistently replace a, wherever a appears, you replace it with that symbol. Okay? So, in this formula, if I replace and b by b prime, I get back the same formula. Except that the variable names have changed, but the formula has not changed. Okay? When you take a formula, you make it go through a transformation, and then you get back the same formula, except that the symbols change. That's all. And nothing else changes. Then that expression is said to be an invariant expression under the transformation that you have used. Okay? So if I take a cube and you can see only the front face of the cube, then if I turn the cube 90 degrees, you will not be able to say whether I had turned the cube or not. If you had not seen me turning the cube, you would not have known that I have turned the cube. Okay? In mathematical language, that is what I'm saying. The transformation is I have taken some action, but I have not told you that I have taken some action, and I'm showing you the thing, and you will not know that any transformation was done on it.